Hi everyone, thank you for attending this talk. Please be indulgent because that's the first time that I am alone on stage, so we'll try to not make too much mistake. So today I'm going to talk about data structures for data science, and more specifically xtensor, which is a lazy tensor algebra library. First, a few words about me. So I'm a scientific computing software developer. And before I joined QuantStack last year, I was a quantitative developer at HSBC. So then I joined QuantStack. I co-authored xtensor, but also XSIMD, which is a wrapper around SIMD intrinsics. I also co-authored Xus, which is a native implementation of the Jupyter kernel protocol that we will present at the JupyterCon next August in New York City. Before I get dived into what is xtensor and how it works, I would like to bring a little bit of context about why we are doing what we are doing. It's not because we can do it. It's also because there is a real need for such library. So the three main languages used in data science are Julia, Python, and R, which together gave the name Jupyter. And they all have the concepts of multidimensional arrays and data frames. Now the problem is that they don't interpret very well. I mean, they have slightly different semantics. They have incompatible in-memory representation. And so just complicated to instantiate, let's say, some data frame in R and work on it and pass it to another piece of software that is written in Python or Julia. In 2015, key developers from the R and Python communities, and also for Julia, I'm not sure about that, gathered in Berkeley for a workshop about data structures. And their goal was to discuss how to make all the ecosystems work better together. And they came across the conclusion that they need to enforce common formats and protocols to communicate and store these data structures. And of course, there would be the need to support natively these protocols across all three languages. So that means that you should be able to instantiate, let's say, data frames in R and work on it, and have the same data available on, let's say, in the pandas, for instance, without any copy or things like that. But one of the most important conclusions is that all these three languages are built upon C or C++. So it would be cool if we could converge on a common native C++ implementation of these data structures and provide bindings to other languages. So to come back to the war of languages that Sylvain mentioned this morning, it appears that C++ has won. So what we need here is one tensor to rule them all. What would it look like? So the first requirement would be to be as cool as NumPy. As Python developers, you are all comfortable with NumPy and its API. So having a library unifying all the tensor libraries with similar API would be fastly adopted. Another requirement would be to enable the use of already existing data structures. I mean, you can claim for interoperability and say, well, I can work with already existing libraries. The goal is to rule them all and not only the dwarfs, so get to do some interoperability stuff. And last requirement would be to enable transparent use of large tensors backed by other things that just in-memory containers. That could be database, that could be file system, that could be calls across the network. So you can't have libraries that is just an in-memory representation of the data. This tensor should be, that should be, sorry. Yeah, that should be just an operation system. So in which we can plug any kind of data structure. And so today, we're really pleased to announce the release of xtensor, which is lazy tensor algebra expression system. So what it is? First, it's a C++ template library for multi-dimensional array manipulation. It follows the idiom of the STL. So for those not familiar with C++, we provide iterator pairs. This allows to reuse algorithm available in the standard library of C++. So a lot of things like sorts and accumulation, things like that. We provide a clear value semantics. So you have real mathematical objects and no surprise when you manipulate them. And also an API, as I said, similar to that of NumPy. Beside that, we provide Python bindings. So that's enable xtensor API on NumPy arrays, which means you can just on Python sites instantiate the NumPy arrays, work with them, pass it to code which is implemented with xtensor with no additional code. We provide also Julia bindings to same purpose but for Julia. We provide a cookie cutter project. So this one is for people who want to start coding the fastest possible. So it just generates a skeleton of projects with bindings to Python and xtensor, so you can focus really on your application code. And all of this is, of course, open source under the BSD license. So, as I said before, the API of xtensor should be really close to NumPy. So there is a non-exhaustive list just to show how it looks. So we could, of course, instantiating and reshaping arrays. We provide building functions, just like NumPy, so linspace, logspace, and so on. We provide views. The syntax is a little bit different from the one of NumPy because of constraints we have on C++ operators, but the semantic is really the same. We also provide reducers, so you can sum or compute the product of the mean of arrays in every direction on the whole array. And we provide, of course, Boolean operations and other mathematical operations. So as I said, this is not an exhaustive list. You can find one on the xtensor documentation. We provide the NumPy to xtensor cheat sheet, so with all the NumPy MPI and its counterparts in C++ xtensor. So even if xtensor provides a similar API to the one of NumPy, it doesn't work the same way, and it's important to understand the main differences in the implementation so you can really leverage on the power of xtensor. So let's say you want to compute a simple formula around tensor with tensor. In xtensor, res here does not hold any values. Nothing is evaluated until it is assigned to a container, like here, or upon access. So res can be accessed as if it was a tensor. It can be assigned to a tensor, but it's not a tensor. So a natural question is, what is res? Little bit of magic, right? So res is an expression, which means it's an in-memory representation of the syntactic tree of your expression. So now, what does it imply? If you write this client code, so the same formula, okay, I would like to zoom, but it's not more than the same formula as previous. With a traditional implementation and operator overloading, you will generate a lot of temporaries for computing intermediate results, which means either iterating over the arrays and also a lot of additional dynamic memory allocations, which are just performance killer. With xtensor, the code that is generated is just like that. So it's just as if you had written the loop with the exact expression inside it. The same is true if you want to access a single element, and it's even worse because you will compute the whole expression just because you need one element. And of course, with xtensor, we generate only what we need. So this is one of the differences. Now that we have expression, we would like to operate on them in a similar way as with NumPy. So first, let's see broadcasting. Broadcasting rules, for those who don't know them, just are quite simple. Just if you want to operate on tensors or arrays who don't have the same shape, you just make one of them appear with the same shape as the other. So you can add a line to a matrix, for instance. So you get this. In xtensor, what we're doing when we broadcast a line to a shape, matrix shape, for instance, we make this line appear as matrix, but we do not copy anything. So we just the memory footprint is the same as the one of the line. And it's also true for expression. So if I want to broadcast a more complicated expression, I will never compute it. I will just take something like a pointer of a reference on the expression in the broadcasting expression, and I will compute it only upon access or demand. Another cool things in NumPy that we also have in xtensor are views. We provide, let's say I want to take 1 out of 2 elements of views. The syntax is a little bit louder, but it's quite simple. What's important here is we do not make any copy. So the view is a proxy over the underlying arrays, which means if I change the value of the underlying array, this change is reflected in the view, and the opposite is true. We provide slicing views. We can also combine slice and range. So we provide also index view as in NumPy, so you specify the elements you want to keep with indexes. Now, for such expressions, if you have a closer look, you can see that all the elements we need are greater than 20. So we provide filter views, so the syntax is shorter. And as with other expression, we can operate on it, and the results of the computing is also seen in the underlying array. Another tool that we provide and that will be needed for building a data index and data frames are missing values. So also quite simple syntax. When we build an expression upon missing values, we can ask for the result of the expression, or also have an expression, a Boolean expression, telling if the value are here or not. So that's for some of the features. There are a lot of other features that I won't present now, because it will just take the whole day, and I think talkers, speakers after me won't be happy about that. So let's go on. So how can I do xtensor? How can I get xtensor? So we provide a conda package. We also provide a Debian package, or you can just install it the traditional way with from source and build it with CMake. You can also try it without installing anything. So this is quite unusual for a C++ package, but so it's built upon a binder, and you can you have a try it now button on the xtensor site. So if you click on it, you will have a C++ notebook where you can try exploring it and have some results. Okay, so this is for the C++ part. Now, as I said at the beginning, one of the goals of xtensor is to provide an homogeneous way to work across Python, R, and Julia. So here I will show how it works with Python. So let's say I want to author Python extensions with xtensor. So the first thing to do is to write your C++ code. So here that is just one line of code. Just want to yes. Oh, okay. Sorry, it's not my computer. So here you get the simple function. So let's say I just want to compute the sum of the side of an array. So the simple functions. The way you expose it to the Python is quite simple, just a few lines of code. We rely on PyParis 11 for that. And the way you call it from Python is really, really simple, just as if it was a NumPy code. So there is really no difference. Another thing you can do is create a universal function from a C++ scalar function, so just like you would do in NumPy. So again, you write your function, so simple formula, and you get a vectorized function with a simple line of code here. Just a single call, and you can call it on NumPy array without any copy. So as I said at the beginning, we provided xtensor cookie cutter. So in more details, this generates a few examples from what we have in documentation on, or in examples on xtensor-python project. It provides unit tests, HTML documentation, at least a skeleton, and minimal setup.py, so you can push your package on PyPy. So what's next? First, bindings with Arrow. So we are actively talking with Wes McKinney to collaborate on this project, so we can plug xtensor on Arrow structure. Also binding with R. They are currently under development, so there is already a repo available on GitHub. Binding with BLAS libraries. Actually, we already released the first version, but it's really, really early stage development. So they are binding with BLAS and LAPACK libraries. And we plan to implement some other algorithms, so such as go-to product and things like that. Also, SIMD and GPU acceleration. So I mentioned XSIMD at the beginning of this talk. That would be used in and plugged in xtensor in the short term. And of course, the ultimate goal is world domination. So, of course, this is not a single-person project. So here are people involved in the development of xtensor. So Sylvain Carlet, you already know him, me. And the third core developer, who is Wolf Precht. So he's a guy who has developed xtensor BLAS, who is working on xtensor R, and who brought a lot of the NumPy functionalities in xtensor. So really smart guys. Another guy who worked a lot of xtensor, not on the C++ code, but more on packaging, is Ghislain Anthony Vaillant, who is a Debian package maintainer, who gave us a lot of help on how to package it, not only for Debian, but also best practices for CMake. So yeah, it gave a lot of help on that. And I think I'm done in advance.